Yeah. Good morning. Okay, sorry. This is morning in Nigeria. This is 1st of October, and I've decided to select a wave equation for the assignment that you gave me. So I'm going to be describing the the thinking behind the modeling that leads to a wave equation, which is the partial differential equation that generally describes the physical phenomenon of wave propagation. So, um, generally, the wave equation is a partial differential equation. Um, we classify that as hyperbolic differential equation. It is a second order differential equation, linear in both time and space. So, the the general idea is not just a simple physics bringing two things together. One is the second law of motion, is the second law of motion, then the other one is the Hooke's law. So um, I am using some simplifying assumption here, but majorly I just assume that we have a very elastic string with uniform mass distribution. I mean, like uniform linear density, that is the mass per unit length. So that to make things easy, I mean, for this derivation, we can assume that masses are concentrated at specific points, equally spaced, I mean, along along the string. Then the elastic behavior is located in between these points where the masses are concentrated. So I have presented a simple diagram. I did all this with mathematics, so I don't know how to relate the border around the position. You have x, you have the position x minus delta x and x plus delta x. So using a given number of these masses, um, we now find that the mass of each of those masses concentrated at those points will be the product of rho and the length divided by the number n that we're using. So rho times length will be the total mass of the screen. Then the length of the interval between any two points where the masses are concentrated will be the length divided by n. So, but for the stiffness, we have to be a little bit careful because now we have strings arranged in series. Strings arranged in series behaves like in a system of parallel. What that means is that the resistance of each of the resistors that you have in a parallel combination is actually higher than that of the combination, that is the total resistance of the parallel arrangement. So something similar happens here when strings are connected in series. The total the stiffness is actually less. I mean, like if each of those strings have exactly the same stiffness constant, then the overall stiffness constant of the string combined together will be uh, the value for one of them divided by the number that you have, just like the mean of reciprocal that you take the reciprocal of that. So if we do that, what that means is the stiffness of each of the member that you have in this argument will be n multiplied by what you have for the total, the actual stiffness of the string that are variables. So now we use Newton law of motion, which is just the mass times acceleration, and then the acceleration here we are using u to represent the displacement of each of these masses. So if the displacement is u, then the rate of change of u with respect to time in the second derivative gives us what? That acceleration. So the Newton law just is expressed in the equation 1. Then for the Hooke's law, uh, we are considering the mass at point x. Then we have a mass at point x plus delta x. We have another mass at x minus delta x. Now, the mass at x plus delta x pulls uh, on the mass at x, towards itself, right, in its own direction, whereas the one behind pulls it backward, depending on their displacement from the equilibrium position. So with that, we can write out an approximate an expression for what the net force will be and the hook force. So that will be K multiplied by the difference in the position between uh, the mass at x with the x and the one at x, then subtract that from the difference between product of K and the displacement of the mass at x and the one at x minus delta x. So that gives us the equation 2. So if we equate the two forces, we have equation 3. Then we do some algebraic manipulation. We end up with equation 4. Then if we try to bring in back the original parameters that we generate, that is, you try to bring back the rho, the actual P, the Stevens constant of the string, the length of the string, we end up with equation 5. Now, we know that we actually got the delta x by dividing the lengths into n number of intervals. So it means as n approaches infinity, then my delta s goes to 0, then the expression in the bracket in equation 5 will actually become the second derivative displacement with respect to x. So uh, from Hooke's law, we know actually that the product KL is dimensionally the same as tension. Not exactly the same. The reason here why we ended up with KL is because the difference between u at x minus delta x and u at x is not actually the extension. So it's actually part of extension and the part of the length or the original length of the string. If we have used extension, we will end up with only extension in equation 6, and that will directly mean the tension in the string. But the analysis still work fine. So just tell that dimensionally, what we end up there, with in that equation 6, that is the KL, is actually representing tension. So the ratio of tension and the linear density of the string is the square of the velocity of propagation of the wave. So that gives us equation 7. And that's complete derivation of the differential equation that governs with propagation in the medium. So we now talk about the solution. The solution solving a differential equation numerically is almost like working back to how the equation was derived originally. So but here I like to break the differential equation down into two known equations. So, one, I will have instead of dealing with second order differential equation in time, I will not be dealing with two first order differential equation in time. First, I express the velocity as the rate of change of u with time. Then I express the rate of change of the velocity with time as this product of c squared, which is the velocity of vibration, and the second derivative of u, which is displacement with x. Alright, so I don't want to deal with the issue of CF a number here, so I'm not going to be discretizing explicitly. So I'm going to be using fully implicit discretization. So if we discretize equation 8, we end up with equation 10, and if we do that for equation 9, we end up with equation 11. So I'm going to be using m and n for my space and time counting. So if I say n plus 1, so I'm actually moving from equation x to equation x with delta x. And then if I say n plus 1, I'm actually moving from type t to type uh, t plus delta t. All right, so that's so equation 10 and 11 can be written as to what you have in 12 and 13 using m and n. So now in the programming, uh, all the parameters that that will be used in solving this equation will come through the argument var. I have attached a picture of the program here. Everything is just about 22 lines. I made this really short so that everything can fit into uh, the window. That's I think this window is kind of a little big. Okay, I zoom. Let's zoom out a little. Okay. I think it should be fine like this. All right. So you can see this. So everything coming through the variable var, which is actually a struct. So it contains the number of points I want to use in the calculation, that is discrete points, the length of the string, so it contains the left boundary condition, the right boundary condition, uh, the initial displacement, so which means I can change the initial condition, so initial displacement and then initial velocity. So uh, okay, that's all. Then I have the C, which is the like wave transition velocity, and the time step that I want to use. So I listed some variables as global variables. These are variables that I'll be using in other functions that will be called while the calculation is going on. So all the variables that I will be using were described, assigned between line 4 and line 6. So the initial displacement is a function of x, the initial velocity is a function of x, uh, uh, the right condition, that is the condition of the right hand, is a function of time, and the one for the left condition. So all these are function handles, so they are all attached in the struct var. So then at line 7, I make the string. That is after creating the x grid, that is my x location. So I have the u values, which is the initial displacement that's been calculated. So I supply that with the left boundary condition upon t equal to 0, the right boundary condition at t equal to 0. Then the function make string, then creates the string. All right. So now we enter the while loop of line 8. Then the next thing in line 9 is first to update the time t. Then I compute the left boundary condition, the right boundary condition. Then I set the u and the v already computed initially to the values at the previous time step. I want to calculate the next time step now. So I make that into a column vector, then I send that into f sub with a residual function to be solved. Now the residual function is the algebraic form of the differential equation. After discretization, that is we have equation 12 and equation 13. So what happened is I wrote it in the residual form by bringing everything to the left hand side and equating to 0. So the job now is to find the values of v at n and n plus 1, the values of u at n and n plus 1 that satisfy equation 12 and 13. So then when f sub is done, I have the results in wave uv, then I extract the u and I extract the v, and then I update the string just so that I can see how the string is behaving as I'm solving the equation. So in line 15, that is the mixed string that created the string that shows how the wave is propagating. Then the residual here, I've used anytime I have the opportunity to use my method of vector indexing, I like to use. So here I have used the vector indexing method. So since the boundary conditions are known, they come in, I attach them to the U, right? Then I just do vector indexing so that I don't have to go through the loop to calculate the residual. at each grid point. So I send that into the while, and that is what is used by fsolve to calculate the correct value of u and v. So that is a brief explanation of everything I the code. It's just about 22 lines. So then to do the simulation, so I have this set of parameters here that I used, and I created a script uh, for for the simulation that calls the transverse wave code. So when you run this, you'll see the wave propagation. So I am going to do that now, and then so that you can see how um, how the code works. So we can make changes to any of these and then see the behavior. So first, I'm setting the initial displacement to 0, initial velocity 0. I have the left boundary condition, I have the right boundary condition. There are two forcing functions coming from the left and the right. So if we run this, um, then you can see how the wave is coming from the right and then from the left and then out from the right too. So um, we can make changes and then see how the solution works. For example, I can start this and say, okay, for example, let us assume that the right boundary condition is actually 0. That is, the string is fixed on the right. So that's can be this, and then comment the rest. So if I run this code, so this is what I see. uh, this shows that the right is fixed. Then you see the stationary wave behavior, that is the reflection of the wave as it hits the right boundary and it's then reflected back. And then you now have you have a stationary wave behavior. So thank you. For this is the end of the demonstration. I will now email this video, the code, and then the PDF that I need. So there is something that I need to address. Um, I'm actually applying for a PhD position. I got scholarship to do my PhD in Cambridge in 2015, but I dropped the program after 1 month because my mother was really sick and I wasn't able enough to continue to pay her hospital bill. So I came back to Nigeria. I took up a job as an applied mathematician and I've been taking care of her since. But thank God that now she's fine and she's okay. So I guess it's the right time for me to go back to study.